Hi guys, hi Valentin, hi Dmitry.
Hi, Roman.
Hi guys.
Okay, just a second. Before we start the conversation with you guys, I just want to say that this is the channel where you own a YouTube channel, Jacob, where the recording of all the talks would appear shortly. Not shortly, but after some time after the conference. So if you want not to miss these talks, please click subscribe button. Also, in the future on this channel, we will conduct more webinars and other stuff, which should be interesting for you if you're a Java developer or somewhere in the Java world, like Kotlin, Scala, etc. So please subscribe to this channel if you want not to miss it. Also, I see that we have now 23 likes. That's wonderful. I want more. So please guys go and like this video. This will be really nice. Okay, now we have in our virtual studio our next speaker, Valentin. Hi again. Could you please tell us, like in few words, what your talk would be about?
Sure. So my talk will be about distributed databases, generally speaking. Distributed databases is something that is definitely becoming more and more popular nowadays. So it's practically everywhere. One of my favorite examples is online banking, right? Like 10 years ago, we used to go to a bank to do pretty much anything there, get cash, check balance or whatnot. Now you do everything from a mobile app. So what used to take several hours at best now takes several seconds, and therefore, the load on the IT infrastructures increased dramatically. We need scalability, we need performance, and that's what distributed databases and distributed systems in general provide. So what I will do today is basically go through major components of such systems and show how they interact with each other and how these kind of systems work under the hood, so that there is some understanding around how the system functions, so that you can get the most from these kind of systems. Because it's important to kind of understand at least a little bit, at least on a certain level, how they work under the hood, to get the most from that.
Okay.
Do you develop, by the way, distributed systems on your own? And how long?
Yeah, so I work for GridGain Systems, and I'm also one of the committers of the Apache Ignite project, which is essentially a distributed database. And at GridGain, we also base all our products on Apache Ignite. And I've been doing this for 10 plus years. So I hope I can share some of that experience today.
How did you came to that area? I mean,
that's just pure luck. Nothing more than that. Yeah, that was like, back in 2010 or not? Yeah, 2010. So I was just looking for a job, and I stumbled upon GridGain, which was a very small startup at the time. And it was, if you remember, it was a very hard time, actually. I couldn't find a job, literally. And I got an offer, which was quite a big surprise. And as a matter of fact, at first I was not even working on core products. This was some side project that the company was doing. But then, eventually after a year or so, I transitioned to the core product, and, that's basically where it all started.
I think I just want to say that when Vali, you say that like you work for Apache Ignite, Dima should do something like this.
Yes.
Because,
do you mean that?
yeah. So something like that. So it's not a secret. You both guys are one of the main contributors to Apache Ignite, from what I know. Once I was also a contributor to Apache Ignite, so I see both of you in these letters, which I receive a lot for that time. So hope this would be really useful for everyone. I just have a small question, like a fast one, because we have not a lot of time before the talk start. So could you tell us with the secret? The Apache Ignite exists for a pretty long time. What's the secret? Why it's more or less popular?
Well, I mean, as I said, there is a lot of demand right now. I think Apache Ignite is kind of a cutting edge technology, which again, I mean, I actually wish it was more popular, and I think the popularity will increase over the time. I would not even say that right now it's much less popular than many other databases or many other systems. But what Apache Ignite does is basically attempts to do that other systems don't do. One of the main focus, for example, is hybrid workloads, right? Basically, the combination of transactional workload and analytical workload. This is something that many companies are struggle with and are looking for solutions for. And Apache Ignite is basically one of the very few products that try to address that. So yeah, I mean, I think as long as we do our job well, it will become more popular over the time. Actually, at least I hope so.
Okay. That's great. Anyway, so let's not waste time anymore. Let's start the talk. Good luck.
Thank you so much. Yeah. So as I said,
you share,
sorry.
I
need
to
to
share your screen.
Yeah. Yes. Sorry about that.
No worries. We're here to help.
And
yeah, guys, while we're sharing the screen, I want
right.
to remind you that we have special Telegram chat. The link is already in YouTube channel. So go to this chat and post your questions there, and we will ask these questions to Valentin. That's it. Good luck with your talk.
Thank you so much, Roman. Thank you. Yeah, so for, I don't know if there is anyone who just joined. So today I want to talk about distributed databases. Distributed databases is something that gets a lot more traction nowadays, becomes more and more popular, and gets more and more demand from many different companies around the world. And the reason for that is the world is changing. We have a lot of applications that are accessible by more users. I've just described an example of online banking. Nowadays you can do everything, or basically any bank operation from a mobile app, and therefore there are much more requests coming in into those IT infrastructures that those banks run, and there are much more data that they need to store, and so on. So all that creates demand for higher performance and, what's even more important, higher scalability, because those systems, they need to handle more requests, they need to store more data, and so on. So distributed databases is essentially a class of products that provide this kind of scalability and this kind of performance. And but the main challenge with this kind of systems is complexity. At least for now. It might change in the future, but for now, it's quite hard to add a distributed database into your architecture. And unfortunately, it's not like you just add it there and you point your application to a new database, which is now a distributed database, and everything magically works and everything is faster and you're good. Unfortunately, that's not the case. Unfortunately, you need to figure out how to data model for this kind of systems, how to properly, maybe rework your applications and whatnot. And in order to do this properly, you need to understand, like, instead of treating it as a black box, you need to understand, at least on a certain level, how they work under the hood. So what I will do today, in order to kind of describe the main components of this kind of systems and how they interact with each other and how those systems work, I basically will create a very simple database from scratch, a distributed database in Java. Of course, it will be very kind of primitive database with very few operations available, but nevertheless, it will be functional and it will demonstrate all those main concepts. My name is Valentin Kulichenko. I work for GridGain Systems, which is a company that based all products and all services on the open source Apache Ignite project, which is a distributed database with all the different capabilities. At GridGain, I do product management right now, although I've been doing development and customer support and many other different things. And that's basically my whole career. I work with distributed systems for 10+ years, and I hope I will share some of this experience with you guys today. All right, so let's get started. And we'll get started with defining requirements for this new database that we're going to build, because that's always important. And there are several important requirements that I want to point out. So the first of all, data storage. We will store data in memory. First of all, for simplicity, I don't want to worry about the complexity of disk-based storage here. But also, it's actually something that gets traction as well. More and more databases are based on in-memory storages and in-memory computing and all that. So it's kind of important as well. So the second requirement is very basic key-value API. Again, different databases, they provide different APIs in key-value, SQL, different compute capabilities and whatnot. Again, I'm sticking to simple things here. So I'm just doing key-value API with only two methods, put for writing the data and get for reading the data. And I will only work with string data types, again, for simplicity, not to worry too much about complex serialization protocols and whatnot. The third requirement is scalability, which of course is the requirement for distributed systems. It is probably the most important requirement. And by scalability, I basically just mean that we want to be able to run multiple computers that are visible to the applications as a single database, right? So the application doesn't have to worry about how many computers are there, how they're connected to each other, or anything like that. Application only knows about those public APIs, right? But the system itself internally provides scalability. And I want to be able to add more computers into the system, remove computers from the system, and do that in runtime. Other two requirements, 4 and 5, are also relate to scalability, because scalability basically it has two aspects, right? The first aspect is what I call computational scalability, meaning that we want to process different requests on different nodes, on different computers, right? So if you have an application that creates 1,000 TPS, for example, 1,000 operations per second, we want 500 of them to be routed to the first computer and 500 of them to be routed to the second computer. That's on a two-computer cluster, on a two-computer database. And that needs to happen automatically by the system itself. Again, application doesn't know about that. Application only invokes public API methods, and then requests automatically routed to different computers in the system. And the second aspect of the scalability is data scalability, meaning that we want to be able to store more data by adding more computers. So let's say we have 100 gigabytes of RAM on every server, and I want to be able to store 300 gigabytes of data on 3 computers. And if my data set grows, it's now 500 gigabytes. I just add 2 more computers, I have 5, and I can store that data. And again, this has to happen automatically by the system. Application should be agnostic to the fact that different data is stored on different computers. Again, it just invokes public APIs, and that's all. So these are the requirements. So let's start with first two, which are just very basic, first basic requirements. So we'll create the data storage and the API for the data storage. And what I will do is I will basically create an architecture step by step by adding more and more components into the system. So this blue box here, the big blue box, basically represents a server-side process, a process that we will run on every computer in the database, server-side node. And the first component within that process is, of course, the storage itself. So the storage basically will incorporate some underlying structure, which in my case will be just a simple concurrent hash map, because the data is in memory, and also we only have key-value API, so we don't need anything more complicated. Obviously, in a more mature, more functional system, you will have more complex data structures under the hood. In order to access this storage from a remote client, we need to have some kind of a communication layer, which will be responsible for all the networking, all the creating the sockets, listening for connections, accepting them, maintaining those connections, and it will also be responsible for certain serialization protocol between server and the client, so that they know how to talk to each other. And the same will happen on the client side, right? So this green box is my client, which will be embedded into a certain application. And the client has, of course, the same communication layer, which implements the same communication protocol. So that, again, it knows how to communicate with the server, it knows how to send a put request or a get request or anything else. And then there is the public API, which basically just exposes those public APIs that can be invoked by the application. So what will happen is that application, whenever application wants to do something, write the data or get the data, it will go through the API, and the API will access the server side through the communication layer. And on the server side, the storage will be either updated or read, and will then get back to the client with the result. So it's not a distributed system yet, of course. We have only one server process, but it's a start. And I didn't mention that. So I will also go through the code as well. So I have kind of a project which already implements everything that I'm talking about here. So I will go through the code. I will show you how it actually looks in the Java code for a little bit more understanding. And I will also run a couple of tests to demonstrate a couple of things. So as I said, right, so this is our first iteration. So we only will have a server with the storage and the client with the API and the communication layer between them. So the storage, again, storage is very straightforward, right? So we have this concurrent hash map data structure, which is my underlying data structure that actually stores the data. And it has put and get methods, which basically just delegate to that concurrent hash map. And these are not public API methods yet. These are just my kind of private API that is used by other components, in particular by the communication layer, which is implemented here in the communication class. And this one is also pretty straightforward. It uses kind of, basic vanilla Java API for networking, synchronous communication, thread per connection, very simple stuff. Of course, a real system will approach this differently, but again, I do a lot of things here for simplicity. So the important part is in this listen method, which implements my communication protocol and the way they communicate with each other, right? And it's all based on this request interface, which is sent by a client. So client sends an instance of a request interface that corresponds to certain operation that it wants to execute. And this request has the handle method, which gets the storage. So any request will implement this handle method with the storage, and it will implement the actual logic, right? So for example, the put request, it has the key and the value, which is sent along with the request itself. And when the handle method is executed, it delegates to the storage, and this way the value is written into the storage. So the server class kind of wires it up.
So seems we have some technical problems. Yeah, let's wait just a couple minutes while it will come back to us. Yeah, I hope it would happen soon. Yeah, I'm here still, so you know that the broadcast is in progress and everything is fine. Well, fine. So yeah, let's wait a bit while Valentin will come back to us, and we will of course proceed with his talk. Do we have Dima on the call? May I ask our video operator to bring me Dima to virtual studio?
Yeah, I'm
Yeah,
here. I'm here.
yeah, cool. So while while he's reconnecting, yeah, we may wait for him to give. Oh, okay. While he's back with
What
us.
happened?
I don't know. You just freeze. You just freezed.
Okay. Sorry about
So
that.
could you
I
please
don't know what
share your
happened.
screen and we will proceed.
Yes. At what moment did you lose me?
Uh, that's hard to say.
Okay.
So I think
all right.
just
I guess we lose 40 seconds, not more.
Okay. All right. So I guess it was it was when I was showing the code, right?
yep.
Okay.
Yeah.
All right. Okay. Yeah. So yeah, I don't know when you guys lost me. So let me just very quickly go through those classes that I went through. So again, this code basically just represents what I'm building in this architecture. So it has all those components that I'm describing, right? So we have the storage, which is very straightforward. It has the concurrent hash map, which is my underlying data structure for storing the data, and it also has method put, and method get, which are not the public API methods yet. These are just my private API methods, which are used by different by other companies within the system, and in particular the communication layer, which is implemented here. And communication layer is just uses basic Java networking APIs to communicate, and also implements its own communication protocol through this request interface. And request interface, so basically, client always sends an instance of a request interface, which implements certain logic within this handle method. So, for example, if we take a look at the put request, it has the key and value that are coming in along with the request. And then when the handle method is invoked by the communication layer, it delegates to the storage, and this way the data gets updated. And the server class wires it up with the instance of a communication component, instance of the storage component, and there is the start method that initializes everything and starts everything. So in the client side, it also has the communication. The only difference is that we don't need to invoke all those start and listen methods because we don't listen to any requests here. We only send requests to the server side. And we have the put and get method, which is my public API methods, which are invoked by the applications. And those methods, they go through the communication and they send requests based on the operation that those methods want to execute. So, for example, the put method will invoke this execute method, providing the put request with the key and the value. And also, we need to provide the address. And for address, for now, I just hard code the default, like the local host and the default port number. So that will change in the future because, when we add the automatic request routing, but at this point, it's just the default port number. And this main method here in the client basically demonstrates how the application will look like. So we'll create a new instance of a client, we will start it here, and then we can invoke those API methods that we have here. Like, for example, we can do several puts, and then we can do several reads. So let's try to run something. So I'll start a single server instance, and then just run a client, and we'll see that it can connect to the server instance and execute those operations. Hopefully it doesn't take too long. All right, I think we're good. All right, so the server is starting. So it doesn't really do anything right now. So the output is empty. Let's start the application and see if it connects, just to verify that everything works as we expect. For some reason, it takes a little bit longer than usual. I apologize for that. So yeah, I didn't mention that it basically just prints out the values that it read. So it does several puts in a loop, and then it reads the same keys, so that we basically read the data that we have just written, and we expect that we will get the those values that we have just written. So we see that we have all the correct results, and on the server side, we also can verify that they've been processed. Looking at this output on the server side. So this is obviously very basic stuff so far. It's not a distributed system yet. It's a single server node and just a single client. It's a good start, but let's actually move on to the fun part and implement, add scalability to the system and make sure that we have a distributed system that can be based on multiple computers acting as a single instance, and that we can add more nodes and remove nodes from the database. So for now, we have this one server process, right? So basically, if we add more computers, we simply will start the exact same process on all those computers. So we will kind of replicate it this way. So let's add one more. So again, this is exact same thing. It has the same storage, it has the same communication layer, all the same logic, and the client can basically connect to them based on their addresses. But for now, it's not a cluster yet, right? Because those server nodes, they don't know about each other. They are not aware about each other's existence, basically. And the client also doesn't know anything about the cluster, doesn't know how many nodes are there. It doesn't know where those nodes are located, and it doesn't know how to connect to them. So basically what we need to implement now is some sort of mechanism that will maintain all this information across all the nodes within a single cluster. So every node in the cluster has to know how many nodes we have in this cluster, where those nodes are located, and it can also contain any additional information like additional attributes or whatnot. So for that, in order to achieve that, we'll add one more component, which is called discovery, whose responsibility is basically exactly that, to discover nodes within the cluster, right? And as I said, basically the whole goal here is to maintain a certain set of information across all the nodes. And therefore, we need some kind of a meta storage that will maintain this information. So the way it's implemented differs obviously from a database to a database. Any mature database will typically incorporate something internally, provide something out of the box for that. But we can also use an external system. Like in the Java world, for example, we have Apache Zookeeper, which is a very good fit for this kind of purposes. In my particular implementation, I will be using a database which is called etcd, which is actually fairly similar to Zookeeper in that regard. It is also like a very simple key value storage, which kind of replicated key value storage, which allows you to store this kind of configuration data, and it allows you to listen for updates so that we can maintain the information consistently. So what will happen is that any node that joins the cluster will first read the information from the etcd, which will essentially at that point will have the list of currently running nodes. Will also subscribe to events, meaning that when anything changes, that new node will be notified if a new node joins or node leaves, and then will write its own information into the database. And when it writes its own information into the database, all the nodes that are currently in the topology will get that notification through that listener that they had already created previously. So this way, we basically, on every node, we will have all the information required, all the information about the cluster that we might need. Again, the list of nodes, how many nodes we have, where those nodes are located, like IP addresses, port numbers. And this way, the cluster will, the nodes will discover each other within the single cluster. Now, the client, it technically can connect to different nodes right now, but obviously, it doesn't have this information as well. So we want the client to have this information too, because otherwise the client, doesn't know where to connect and where those nodes are. And for that, we'll do exactly the same. We'll just add this discovery component to the client as well. It will connect to the same etcd database. It will get the information from there, and it will essentially work in the exact same way. The only difference is that it will not write its own information into the etcd, so it will not register itself, of course, because we don't want client to be a part of the cluster in this sense. We just want to get the information from discovery, to have this list of nodes on the client side, and make sure that this list is also updated when something changes, right? So let's do that. Yeah. So I basically just have several branches here which represent all those different stages, and I will just briefly show you the code for discovery, which has a little bit of a boilerplate, mainly because of the etcd APIs, which are a little bit convoluted, but it basically goes through all those steps that I just described. So first of all, we have this topology map here, which is quite important. So this map is basically local representation of this of the current cluster topology, right? And the whole goal here is that we have the discovery component running on every node, and this component is responsible for maintaining this topology map consistent with all other nodes, right? So whenever something changes, this map must be updated on every single node. So what will happen here is that we will connect to the, and that's the join method, by the way, which is invoked on the startup. And we get the local port here, which is the one that communication uses, and the local ID, which is just randomly generated. I'll show that in a second. And here we go through those three steps that I've described earlier. So we first get the current topology. So we go to the etcd, we get everything that we have there, essentially the list of nodes that are currently up and running, and we update this map. Then we create a watch. Watch is etcd functionality, which is basically this listener, which will be invoked every time something changes in the database. So we'll kind of listen for updates, and whenever something is added, we will add it to our local map as well. And finally, as a third step, we register our own local node in the etcd database by writing this information there. And as I said, when this put happens on the new node that joins the topology, this listener here will be invoked on nodes that are currently there. And this way, this topology map will be maintained consistent at all times across all the nodes that we have. And so on the server side, we just basically have this component here injected into the whole picture. And in the start method, we'll get the port number from the communication, right? So the communication creates a server socket, binds to a certain port number, returns it here, and this port number is then forwarded to the discovery join method and is written to the etcd database. So this way, all the nodes know where those nodes are located and how to connect to them. So, and of course, usually, in a real system, you will also have the IP address and maybe some other information. Here I'm using only port number just because I assume that everything runs on the local host. But IP address is obviously also kind of a minimal thing that you will have to write there if you run in a real cluster. So on the client side, same thing. So we have the discovery just created here. It also joins the topology. I use the same join method, but I don't really join it because I don't provide anything and I don't write any information to the database. But again, I will get all the current state and as well as those updates through the listener that I also create here. All right, so so for now it doesn't really do anything because as we can see, this discovery component is not really used by anyone. So we achieved scalability to a certain extent this way, in a sense that we currently can start multiple computers and they will join the cluster and they will maintain this information and they will aware about each other. And then we can start a client as well that will also have this information. But this information is not used in any way right now. So we will use that for automatic request routing and automatic data distribution. So let's start with the first one. Let's start with the request routing. So what happens is that now we want different requests go to different nodes, right? Based on certain criteria. So the application invokes, let's say, put method with a certain key value pair. And we want to have a mechanism within the system that will decide on which node to send that request, either to node 1 or node 2 if we have 2 nodes. So we'll do that based on the key. And we'll add the following to the client side. So the client, again, as I said, we don't use the discovery information yet. And we obviously want to utilize this information. But the question is how, because discovery just has a simple list of nodes. That's all it has. It doesn't provide any information about the mapping between keys in those nodes, and how those keys should be routed between the nodes, nothing like that. So we'll incorporate that logic in a yet another company that we'll add here. We'll call it mapper. So this company will be responsible for all those things. So whenever the application invokes an API with a certain primary key, it will first go to the mapper and essentially ask the mapper, like asking for the node where this key should be stored or processed. And the mapper will go to the discovery, get the full list of nodes, get the current topology, then do some magic there internally and return the address of that node where this key should be, where this request should be sent to, rather. So the question is what the magic that we're talking about here is. If you think about, if you've been working with, I'm sure you have, with different data structures like hash map or whatnot, you probably already thought about hashing, which seems to be a very good solution for these kind of things, and we'll be using hashing here as well. And we'll start with a very simple hashing mechanism that will provide consistent results. So we'll just calculate the hash code based on the key. We'll also get the absolute value because we don't want negative values in the picture. And then we'll just apply the modular function based on the number of nodes that we have in our topology. So this way, so that will essentially give us an index of a node in the list, right? So if we have 3 nodes, we'll get either 0, 1, or 2, and this way we'll pick the node from the list. So as long as the topology doesn't change, as long as we have the same number of nodes, this will always give us the correct consistent result for any key that we might provide. So that's what we're looking for from this hashing function. So let's take a look at the code, see how it looks like, and we'll also run and see how it now works as a distributed system, not just as a single server in database. So so what changed here is we have this mapper now, which is the implementation of our hashing. function. It depends on discovery, so we pass it through constructor here. And within the node method that basically gives us a node descriptor based on the key, we implement the exact same logic that I've just talked about. So we get the topology, we get the hash code, apply the modulo function based on the topology size, and then get the actual node descriptor based on the index that we got from there. So on the server side, nothing changes. But on the client side, we do have the mapper component injected here, and it gets the discovery that we already have. And what's important is that within the put and get methods, we now use this mapper to get the address of the node where we want to send a request. So instead of hard coding the address, that's what we had before. We go to the mapper, we get the node for the key, and then we get the address for this particular node, and therefore we send a request based on this hashing routing mechanism rather than just hard coding the address or choosing a random one or whatnot. So let's see how it works. For that, I will restart a server. I will start a couple of them actually. So that's my first server, and we should actually see the output from discovery now, because it essentially basically just prints out the topology. So yeah, we see that there is only one node. And when I start the second one, it should show me the two nodes that we have in topology. So that's the second server node. It goes to etcd and then shows me that I have two nodes, which is what we expect. And if we actually go to the first one, we'll see the same thing. So this watch mechanism updated the information in the first node as well. So essentially, this means that we have this list of nodes maintained across the cluster, which is what we expect from discovery. So now let's run the client, which now does the mapping routing based on the hashing function. So we should be able to see different requests processed on different nodes, right? So we have all the correct results on the client side. And if we look at the first server, we see that it processed only 5 put requests and then 5 get requests for the same keys, right? So regardless of which operation we execute, for a certain key, we'll always go to the same node, which is, of course, what we want, because that's where the data would be, because that's where the data was inserted by the put operation. And the second server does the same, but for other 5 keys that we have in the list. So that's all good. So we this way we achieve the routing. However, there is one issue. So let's see how the system behaves if we add more nodes. So remember, by scalability, we not only mean that we want to have multiple computers running a database, we also want to be able to add more computers in runtime without any downtimes. So let's add one more server and see what happens in that case. So I'll add another server instance, server process. It should show me that we have 3 nodes. We do have 3 nodes, and that should be updated on all other nodes as well. So that works correctly. And now I will run the client, and the only difference would be is that I will remove the update operations from here. So it will only do the reads, right? Because the data is already there. I didn't restart any server node. I do have the data in the database. So I can just, I expect that I can just run get operations and get all the data from there. So let's see what happens in this case. And of course, while it compiles, we can probably expect that something will go wrong because the mapping changed, right? So we added more nodes, and the hashing function that we have, it depends on number of nodes that we have. Therefore, the mapping changed. And now the get operations, they go to the nodes where data is not stored. For example, to this new node, which processed like 3 of the get requests, but it doesn't have any data yet, right? Because we didn't execute any put operations here, and therefore nothing was stored in the storage of this particular node. So any get operation that comes here will just return null because storage is empty. So let's fix that, and that actually brings us to our last requirement, which is automatic data distribution. Because basically, if you think about this, we achieve data distribution to a certain extent by adding the request routing, because we route we route put requests to different nodes, right? And therefore, data is being stored on different nodes. So we kind of distributed the data. However, it works only as long as topology doesn't change, only as long as number of nodes doesn't change. Should we add a new node in topology into the cluster? Everything is broken. We get inconsistent data and all those problems around that. So let's see how we can fix that. So this is fixed with a process which is usually called data rebalancing, which is essentially the process of data reshuffling and data redistribution in case of a topology change. So let's see how we can implement that. So as a first step, Discovery will notify the storage. So this is a very straightforward step. Discovery has all those events coming in through the etcd watch. So it will just redirect the notification to the storage. So we need to let storage know that topology changed and that storage needs to do this data reshuffling. So storage will get the notification, and then it can go through the data and see what needs to be done. And we want this to be, we want the resulting data distribution be consistent with the way how we request the route the requests, right? So remember, we routed those get requests to the new node, and they got us empty results because there was no data. So we want that data to be there, right? So we want our data distribution to be consistent with the request routing mechanism that we use. Therefore, the storage will use the exact same mapper and the exact same hashing function that we had on the client. So for every key, basically, the storage will check if this key belongs to this local node or not. If it does, it will keep it. If it does not, it will send it to the node where it actually belongs, because mapper will provide this information. Mapper will tell where this particular key actually should be stored. And then through the communication layer, we'll do this data exchange across the nodes. So this red arrow just shows the whole process of sending the data back and forth in order to achieve this proper distribution based on the new topology. So that all works, and that's all good. But the only issue here is efficiency, because I've just mentioned that the storage will essentially go through the data and check with the mapper for every single key, which is obviously not super efficient. We don't want this whole process to depend on number of keys that we have, because we might have a lot of them. We might have million keys, billion keys, or whatnot. So we want to optimize this process somehow. To optimize this process and make sure that we don't have this linear complexity, we'll apply a technique which is called data partitioning, which is a very simple technique. It basically implies that we split the data into partitions, into kind of groups. And the important part is that the number of those partitions, the number of those groups we split the data into, does not change. It is constant. So let's say we configure our database to have 10 partitions. and it will always have 10 partitions. Like with 2 nodes, we will have 5 partitions on first node, 5 partitions on the second node. And if we add more nodes into the cluster, the number of partitions will not change. It does not depend on number of nodes. It does not depend on number of keys. It doesn't even depend on whether we have any data in the database or not. So essentially what will happen is that we now can redistribute partitions rather than keys. And the reason why we can do this is because of the properties of the hashing that we get from there. So now to get from key to the node, we need to go through this kind of two-step process. We first need to map key to a partition number and then partition to the node. And for the first step, we'll use the exact same hashing function that we had before. So we get the hash code, we get the absolute value, and then apply the modulo function. But instead of using number of nodes here, we use number of partitions. And unlike number of nodes, number of partition never changes because that's how we designed it, right? So this step will always be consistent. It will never change. Any key that you pass through this hashing function will always be mapped to the same partition because number of partition doesn't change. Hash code is consistent. So we don't have to worry about this. The second step still uses the same mechanism, but this step is dynamic, right? It depends on number of nodes, and a partition can be mapped to a different node depending on the size of topology that we have. And therefore, when we add something, the partition will be moved to the node. But what's important here is that we now work with partitions rather than individual keys, which means that when storage gets a notification, it doesn't have to check every single key. It will only have to check those partitions that are stored there, which is the limited fixed number. And therefore, we avoid this linear complexity of this verification process. We only check 10 partitions instead of arbitrary number of keys. So let's see how it's implemented. So close all this stuff. So, so there are several things here. We have quite a big change here, as a matter of fact. So we have the storage, which, first of all, as I said, we want to introduce partitioning, right? So for partitioning, we basically kind of split our flat data structure into partitions. Therefore, I have this kind of two-level concurrent hash map here. So the top level has the integer key, which is the partition number, and the value there is another map, which represents actual key value pairs for that particular partition, right? And therefore, in put and get methods, we use the mapper to calculate partition number for a key, and then we get the corresponding map, corresponding internal map, and then delegate to that. And the mapper is, of course, updated based on those changes. So we now have this partition method, which uses this very simple hashing function, but based on the local constant number of partitions, right? So it's just set to 10 and it never changes. And then we have this node method, which calculates partition based on node. Again, very simple logic. And the node method, which we had initially, which gets node based on key, it goes through this two-step process that I've described before. So what will happen is the storage, the discovery, now has this listener, which is basically just a runnable, which will be invoked every time the watch is invoked. So something gets updated, we add a new node, we update this in this local topology map, and then we notify the listener. And the server provides the link to the storage remap method here as this listener. So that's the runnable that we actually pass to the discovery. So discovery will invoke the remap method whenever topology changes. And here, what we see is that it just goes through this logic. It goes through every partition. It checks if a partition belongs to the local node or not, comparing the IDs. And if it's not, it sends it through the communication layer using this new rebalance request implementation. And rebalance request just holds the partition number and the actual data for that partition. And whenever this partition is received by the node that this partition belongs to, this onPartition received method is called, and it just inserted into that top level map with all our data. So before we actually run it, I would like to go through one more thing. So it basically covers all the requirements that we have functionally. However, before finalizing, let's go through a sample data distribution, and also which will also reveal one more issue that we'll fix. So as a sample data distribution, let's take a look at how will those 10 partitions that we have be distributed across 3 nodes to start with. Like, imagine you have a cluster of 3 nodes. You have a database which is configured to have 10 partitions. So node index for any partition will be calculated like shown here, based on our very basic mapping function that we've implemented. So what will happen is that we have the list of our partitions, which is just the list of from 0 to 9. And they will those partition numbers will be mapped to nodes like this, right? So it's actually just a round robin distribution. We have 0, 1, 2, 0, 1, 2, and so on. So if we show it on the picture, it will look like this, right? So we'll have some partitions on node 0, some partitions on node 1, some partitions on node 2. Very good distribution, even distribution, so everything looks good. However, let's check what happens if we add another node, right? So we add another node, therefore we have 4 nodes in topology now, and therefore the mapping changes. So let's see how it changes. We have the same list of partitions, but the node indexes are now different. And of course, we have a couple of partitions now mapped to this new node, which has index 3, right? That's the node that we've introduced into the system, and that's actually what we want. So let's so the distribution will look like this, right? Again, every node will have certain set of partitions, and again we have a very good even distribution. But let's compare those two. So this is our new distribution with 4 nodes. This is our old distribution on the top. Distribution with 3 nodes that we had prior to topology change. And we have these partitions 3 and 7 that are being moved to the new node. And that's what we want. That's what we expect from this whole rebalancing process. However, if you look carefully, you'll see that there are a lot of other data movements, and we have a lot of those red errors. And it's basically, at this point, what is going on here? So we have a lot of redundant data movement, which of course doesn't add any value, right? Because the green data movements, they do add value because they allow us to utilize the resources of this new server, new computer that we added into the cluster, added into the database. We can now use it to store the data. We can now use it to process requests. The red data movements, they only consume resources. They consume network, they consume CPU, but they doesn't actually add any value and doesn't actually help us in any way. And that's a big issue, because data movement and the network in general is quite expensive. And moving this amount of data, and like even with this simple example, we have more red errors than green errors. With more partitions, it will be even worse. So moving all this data around will consume a lot of resources, and in the best case, you will get significant performance degradation, and in the worst case, you will saturate the network, saturate the CPU, the cluster will fall apart, you will have a downtime, and all those things that we don't like. So that's a big issue that we need to solve. Let's see how we can fix that. To fix that, we'll change the way we do the mapping. So now to map a partition to a node, we just apply this modulo function, and that's it. So we need a little bit more sophisticated algorithm here to avoid this kind of situation. One of the algorithms that can be used here is called rendezvous hashing. It's not the only one, but rendezvous hashing it's quite popular, and it's also very simple to explain, so I'm using it here. So here's how the algorithm looks like. So we'll assign node IDs to every node. We actually have that. We use UUIDs in the code, but it can be string ID, it can be anything. Just the only requirement that it's unique for every node, right? And we'll then introduce a function h, which will calculate, which is basically a hash function based on a combination of partition number and this node ID. So now instead of just using the partition number itself, we calculate hash based on the partition number and the node ID. And we'll then calculate it for every node ID. So imagine you map partition number 2 to a node. You want to know where this partition number 2 is stored. So you will calculate this function for 3 times for partition number 2 and for every node ID that you have. And you will get certain values, right? These are just random values that you might get, right? So you will have H1, H2, and H3 different value for every node that you have in the cluster. And as a next step, you will choose the maximum value out of those 3. So in this particular case, it's H2. And the maximum value will point us to the server, to the node where this partition should be stored. Right, so if we get the values like shown here, the H2 is the maximum value, therefore the partition will be stored in the node number 2. And you can do this for any partition at any moment in time. It will give you correct, consistent results, just as our previous mapping function. So what's different is the way it behaves when we add one more node. So let's see what happens in that case. So we'll have one more node, node 4. And for node 4, we'll have yet another value here in the list, which is H4. H1, H2, and H3 do not change, of course, right? Because the hashing function is consistent. Node IDs, they also do not change. Therefore, these 3 values are the same. The H4 is the new value. And we basically have only 2 outcomes. This H4 can be either less than Hmax, than the current Hmax, which is currently H2, or it can be larger than Hmax. And of course, there is a possibility of hash collisions, but I'm kind of I'm putting them aside on purpose, because they're typically handled outside of this mapping algorithm by regenerating IDs, for example. So this algorithm kind of assumes that there are no collisions. So as long as there are no collisions, we have 2 outcomes. It's either less than Hmax or larger than Hmax. In the first case, if H4 is less than Hmax, that means that Hmax remains the same. It's still H2, and therefore the partition stays on node 2, so nothing changes. In the second case, if H4 is larger than Hmax, then our new Hmax is H4. So Hmax is updated, right? Which means the partition is also moved, and it's moved to this node 4. So in other words, we only can move the partition to the new node, node 4, or we will not move it at all. So basically, the algorithm itself, out of the box, natively, provides this guarantee that there is no data reshuffling within the nodes that we have prior to topology change. It either moves to the new node or it doesn't move at all. So if we do the same exercise for all those partitions that we have with 3 nodes, with 4 nodes, but with the new mapping function using the rendezvous hashing, we'll see that that's how it will look like. So, right, so we have 2 partitions moved from old nodes to the new node. These are partitions 4 and 8. And all other partitions, they stay put. They do not move. And therefore, we avoid this data reshuffling. and satisfy this requirement of it's called minimal disruption requirement, by the way, meaning that we don't disrupt the system with this unnecessary data movement during rebalancing. So let's take a look at the code for the last time. That will be actually the simplest part, the simplest change, because the smallest change rather, because we only change the mapper, right? So the beauty of this is that we only need to change the actual mechanism, like underlying mapping mechanism that we use, but anything else within the system doesn't change. So the way discovery works, the way the storage works, it works in exactly the same way. We just change the actual way we do the mapping. And all we do here is we update the node method, which calculates the node based on partition, and it implements the algorithm that I've just described, right? So it goes through the nodes, calculates the hash for this combination of partition and ID. And if this hash, and then just searches for a maximum hash, and whatever node that corresponds to the maximum hash value is returned from here. So this way we use the rendezvous affinity function. So I think we're running out of time, so I will not run it. There is the link right here. So if you guys want to pick it up from GitHub and run it on your own, feel free to do that. And I actually would encourage you to do that, of course, to go through the code in more detail, play with it, maybe do some modifications even. And also, if you want to learn more about distributed systems and dive deeper into those technical details that I'm talking about here, because I'm barely scratching the surface, of course, I think one of the best ways to learn is to join one of the open source communities. For example, the Apache Ignite community. I'm promoting the Apache Ignite because I'm part of it, but of course you can pick any other as well. There are many interesting projects out there. So if you want to learn, I would say the best way is to try it on your own, try to work on different tasks that they have there. So you're welcome to join the Apache Ignite community. We'll help you in any way possible if you would like to help. And yeah, so you're welcome. So with that, that's all I've got. And I don't know if we have any time for questions, but if we do, I'm ready to do that.
Unfortunately, we don't have. Yeah, first of all, I want to thank you very much for this awesome talk. It was really interesting, so thank you very much. Unfortunately, we have no time for questions here in broadcast, but we have discussion Zoom room. So links are already in YouTube chat and in Telegram chat. So guys, I saw your questions. Like there are plenty of them. So please follow to discussion zone, and then you would be able to discuss all your questions with Valentin. So yeah, that's a plan for nearest time. So Valentin, again, thank you very much for your talk. I think it was just useful and great.
Yeah, thank you for listening, everyone. Thank you.